I'm Andy Tannenbaum, and I thought I knew how to make this thing talk to the other thing. Normally it works. I've never seen it quite this bad before, but I'm sorry, but I guess there's not much I can do about it. Okay, so I'm going to talk about a reimplementation of NetBSD using a microkernel, and this is the work done by my students and my programmers, and I just sort of watched. Okay, our goal has changed over the years, but our goal is sort of now to build a reliable operating system, okay? So what's a reliable operating system? Okay, let me give you my definition. An operating system is said to be reliable when a typical user has never experienced even a single failure in his or her lifetime and does not know anybody who's ever experienced a failure. In engineering terms, we're probably talking about mean time to failure, 50 years, something like that. I don't think we're there yet. Some people say things are reliable. You know, there's people say, well, you know, if God wanted computers to work, he wouldn't have invented reset buttons. I don't think that's really where we're at. You may think that, but ask your grandmother. You know, I mean, her attitude is, why doesn't it work? Okay, because most other things work. Okay, so let me say a couple of words about what I call the television model. Step one, you buy the television. Step two, you plug it in. Step three, it works perfectly for the next 10 years. Okay, that's what. Although as televisions are becoming computers, this is becoming less so. But so traditionally, this is the way televisions worked. You know, okay. Now the computer model, Windows Edition. You buy the computer, you plug it in. Okay, so we're 2/3 of the way there. It's just this little thing about, and now it works perfectly for the next 10 years. Well, it's not quite there. First, you have to install service packs 1 through 9F. Okay, and then you have to install 18 new emergency security patches that came after 9F, okay? And then you've got to find and install 7 new device drivers, because all the ones they gave you are obsolete. And then you install the antivirus software, and then you install the anti-spyware software, and then you install the anti-hacker software, and then you install the anti-spam software, and then you reboot the computer, okay? Actually, I'm not done. I just ran out of space on the slide. There's more, okay? It doesn't work. So you call the help desk, okay? And you wait on hold for 30 minutes, and then they tell you to reinstall Windows, which is what you're trying to do in the first place, right? And the typical user reaction is something like this, okay, except for us, where it's fun to play with it, but you know, for grandma, it's not fun. New York Times had a thing a little while back saying that 25% of computer users have actually hit the computer because they were so angry with it, you know. It's not the monitor's fault. You're going to hit something, hit the computer itself. Don't hit the monitor. The monitor wasn't, it's not its fault. Okay? So I don't think we're quite there in terms of you know, reliability and so on. Is reliability important? Well, it's annoying when it doesn't work, you know, and there's some lost work. But you should also think about other situations. For example, industrial control systems in factories. You know, cars are moving down the assembly line and something crashes and they got to stop everything. I don't like that very much. Or power grids. You know, power grid goes down for a reboot for a couple of minutes. Get a lot of antsy people about that. Hospital operating rooms. Most doctors like to work in the light. Okay. You know, banking and e-commerce servers. They're down for 5 minutes. You know, they measure the amount of money they lose in, you know, sort of megabucks per minute there. Emergency phone centers. There's a lot of applications. Control software in cars and airplanes and all kinds of things. There's lots of applications where people actually care a lot about, you know, reliability. Is it feasible to make it reliable? First of all, we'll never know if we don't try. The Dutch Royal Academy of Sciences gave me 2 million euros to try, so I said thank you very much, and we tried. Then the European Union gave me 2.5 million euros to give it a shot, so I was very grateful for that, so we're giving it a shot, okay? Okay, is it achievable at all? Maybe you can't make you can't make this stuff reliable, okay? I don't buy that. Systems can survive hardware failures. For example, RAIDs can survive a failed disk. You have a RAID system, a disk fails, it just stops working, makes a big screeching noise, magnetic oxide is flying all over the place, and the whole RAID continues to work, because RAIDs are designed to work even if a drive fails. In fact, you can design a RAID which can survive 2 failed drives if you want. It just requires more redundancy. Memory can fail. ECC memories can recover from memory failures, okay? TCP can survive from packets that get lost. Packet gets lost somewhere, it understands how to deal with that. Well, I didn't get an acknowledgement, I'll send it again. CD-ROMs and DVD drives, 3/4 of the bits on these optical media are error correcting bits. So, a 700 megabyte CD-ROM isn't actually 700 megabytes, it's about 3 gigabytes. And there's a 14-bit number is used to encode an 8-bit number, and then there's a 3,000 byte number and used to encode a 2048 byte sector, and so on. There's many levels of redundancy to make it work. So, if you can survive hardware failures, for heaven's sakes, we ought to be able to survive software failures. That's a lot easier than surviving hardware failures. Okay? So I think we need to rethink operating systems. And the research on this, I think, needs to be refocused somewhat, that performance isn't the only game in town, although some people seem to think it is. We have nearly infinite hardware on just regular generic PCs these days. I looked this up once. I started on the IBM 709, which cost $30 million and filled up a room this size. An iPad is about 30,000 times faster than the fastest computer in the world 40 years ago, and has about 10,000 times more RAM of the biggest computer in the world. It costs $30 million. Okay, there's a lot of power in modern PCs. There's lots of RAM, lots of cycles, lots of bandwidth. There's tons of useless bloatware on all modern software, and so the software is slow and bloated and buggy. It doesn't have to be like that. That's self-inflicted. So to achieve what I would call the TV model, I think future operating systems need to be smaller, simpler, modular, is very important, reliable, and secure, and in particular self-healing, which is, I think, really the key. It's got to fix itself. Okay? Hardware can fix itself, RAIDs can fix their problems, TCP can fix its problems, ECC memories can fix their problems. Why can't the software fix its own problems? It's got to be easier than the hardware. So that's what we're sort of working on. Here's a very brief history of the work we've been doing. I think that Steve mentioned it in the morning. In 1976, John Lyons wrote kind of a commentary on Unix version 6, describing it line by line what it did. Okay? And in 1979, AT&T panicked and said, you can't have students understanding our Unix system. This is terrible. So the new license forbid writing any books about it or teaching it in classes and so on. And then, a few years later, I said, maybe I could write a Unix-like system myself that was sort of like version 7 and didn't have this crazy licensing thing on it. And so I wrote a book, and it came out in 1987, and there was I think, a CD-ROM in the back of the book with all the code. Oh, no, there was before that. There were floppy disks you could get in a separate box, because CD-ROM drives weren't that common yet. So there were like 8 floppy disks, which had the whole source code and everything on it. Then in 97, we made it POSIX compatible, because POSIX had now come out. And then 2000, we changed the license to the BSD license. That previously they were selling the box of things at $69, which was the actual manufacturing cost for the 8 floppy disks and the book about it, and the box and everything. So I convinced them, they didn't understand what they were doing. Convinced them, let's go with the BSD license. We went with that. And then by this time it had been out there on the internet a little bit, but the internet wasn't so big in 1987. As some of you may know, Linus Torvalds wrote in his biography that he had bought a PC for the purpose of running Minix, and he began reading it and began changing it and so on. So in a sense, Linux is a fork of Minix, which is kind of, but of course, BSD guys know about forks. So, the third edition of the book came out. I got the European grant, and then we moved toward embedded systems and toward NetBSD, which I'll tell you about later. Okay, so there's been 3 editions of the book. Okay, intelligent design, at least as applied to operating systems. I have been and always, I think, been attacked for, but I still believe in microkernels. The key piece of software on a computer, the kernel, should be small enough that you understand it. Linux is now 15 million lines. Windows is well over 100 million lines. Nobody understands it. Imagine you're starting at Windows, at Microsoft, and they say, we'd like you to work on the Windows kernel. Here's a room listing 100 million lines, which takes up 18 bookcases of the code. I mean, nobody there understands that. When you've got a product that nobody really understands, it's not a formula for, a bug-free kind of thing. People have studied bugs in great detail. In companies, they often have like registers, and if you make if you find a bug, you have to tell them, and they register it and they log it. People have studied these logs, and getting down to 1 to 10 bugs per 1,000 lines of code is about the best you can do. 1 bug per 1,000 lines of code, it seems to be the best anybody can do. There's been very few recorded instances of actually doing better than that. The Minix has got 15,000 lines of code, so there's 15 bugs in the kernel. We're looking for them, we can't find them yet. but there's a chance we might. Linux probably has 15,000 bugs. Not all of them are serious, of course. Some might be punctuation errors in a message of some kind, but some of them are undoubtedly serious, and other programs have this. Some of you may have noticed that Adobe updates Flash every 15 minutes because of security reasons. Like, they can't get a PDF viewer to work. An operating system is harder than that. And drivers have, studies have shown drivers have 3 to 7 times more bugs than other stuff. I mean, everybody wants to look at the Linux, paging algorithm because it's so much fun. Nobody looks at, the Epson, some printer or, some other printer. Nobody looks at that. And 70% of the code is drivers. Nobody ever looks at that. So that's where the bugs are. Okay. I think a good system should be modular. It should run as multiple processes which are, separated and have well-defined components. So one of our philosophy things is have isolated components. Okay? So move all the loadable modules, also the file system, memory management, everything out of the kernel to separate processes protected by the MMU. And these things then can't interfere with each other too much. Okay? So every module should run with the principle of least authority, the POLA. So if a certain module needs certain power, it should have that power, but it shouldn't have power it doesn't need. There's no reason the audio driver needs the power to fork, right? Because it just doesn't need that, and giving it that power is looking for trouble. So the principle of least authority. Step 2 is to isolate the I/O. So the I/O devices should be isolated from each other and limit access to I/O ports. So in Linux, drivers don't have access to the I/O ports. They have to go through the microkernel to get access. So the disk driver can't actually talk to the disk. So if it wants to talk to the disk, it makes a kernel call and says, I want to write on the disk registers. And the kernel checks, oh yeah, you're the disk driver. These are the disk ports. You're allowed to do it. Go. And it did it. Okay? But some other driver can't write on the disk port. So the audio driver can't write on the disk even if it tries. In a monolithic system, of course, it's not supposed to, but it could technically. And you can get bugs or attacks which allow the disk, the audio driver to write on the disk. So I think it should be prevented by the hardware. And you got to constrain DMA. Okay, so it can't write all over memory. If you have an I/O MMU, you can get some of that in the hardware now. Okay, isolate communication. So don't let any of these pieces talk to any other piece. Have a little table somewhere in the kernel which says this piece is authorized to talk to that piece, and then it's okay. And if you try to talk to somebody you're not supposed to talk to, then it's not okay, and it's not allowed. And also, the kernel has some calls. These aren't the POSIX calls. These are very low-level calls, like create the structure for a process that can be filled in later and so on, and handle interrupts. It's very low-level stuff. Again, it should only be allowed to do the ones it needs to do. So you need like a bitmap saying you can make these calls, and if you make any other one, you get back an error message saying no permission. Okay? There's always a way to restrict the power of the little pieces so they only get to do what they need to do. That's the principle of least authority. Give a component only the authority to do those things it needs to do its job and no more. Okay? So you restrict inter-process communication, restrict I/O, you restrict everything. Also make sure that a faulty receiver can't hang a sender. So if a client sends a message to a server and then the client goes away or doesn't listen, the sender shouldn't hang trying to send an answer that the receiver, the original process is not listening to anymore. Anyway, here's the architecture of Minix 3. So this is kernel, which is about 15,000 lines of code. It handles interrupts, message passing, some of the scheduling, some of the inter-process communication, some of the basics for process structure and so on. And then on top of that, in user mode are all the device drivers, each driver being a separate process. Okay? So disk driver and network driver, they're all separate. And then on top of that are the servers, like the file server and the memory server and the process server, and there's a whole bunch of those. And they're running as separate processes. And then there's the user stuff. Technically, these are all user processes, and the structure is kind of an intellectual abstraction because there aren't like 4 levels in the hardware, although if you had 4 modes in the hardware, one could do this. I mean, the Intel actually does have 4 modes, but we don't use them, so it's more of an intellectualization than physical structure. But the idea is each of these is a separate process protected by the MMU, so it can't do things it's not supposed to do. And so user mode device drivers, every driver runs as a user mode process. They don't have any super user privileges. Disk drivers aren't special in the sense they can violate all the rules. The MMU is turned on, so they're limited to their own address space. They can't execute protected instructions and so on. They don't have access to I/O ports. They don't have access to the privileged instructions. They need to make a kernel call